Hello everyone. Welcome to this tutorial video on exploring the thermal modeling of power switches feature of Simba. This feature can help you to carry out thermal modeling structure of a system, calculate conduction and switching losses, calculate components temperature, estimate efficiency of power converter, design cooling systems such as heatsink. Let's show this from a schematic thermal_buck, which allows to set up thermal modeling techniques, calculates both conduction and switching losses of 1 IGBT, determine junction temperature of the semiconductor, implement thermal network for the heatsink. Firstly, let's observe the thermal library with three important T items. Sources, composed of different temperature sources, RC, composed of thermal capacitor and resistor, probes, composed of heat flow and temperature meter. For example, heatsinks can be modeled with networks of thermal resistors and capacitors. The semiconductors library is also really important because it gathers the major components such as diode, IGBT, and MOSFET, which can be associated with thermal data. Those two combined libraries allow the user to implement its own thermal circuit in order to compute losses, temperatures, and heat flows. Secondly, let's check the buck-chopper power converter and more precisely the IGBT first. If you click on it, you'll observe the RON and forward voltage, which are equal to 0 for ideal behavior. But the main information to check are thermal data and average loss calculation frequency. Those two sections allow to select the thermal datas which need to be used during the simulation and the frequency value under which the average losses are calculated. Of course, some scopes are available for losses, energy, and junction temperature calculation. In order to set up thermal datas for losses and temperature purpose, you'll need to click on Test Bench tab and Thermal Data section. From there you can import thermal library file in .xml format that is currently supported by many semiconductors manufacturers. You can find some IGBT examples with the link in the description. Create your own thermal component by clicking on New button. You'll then be able to fill in all the datas needed, modify and edit the actual thermal datas provided. For any new devices added to the list, you can observe some section to fill in. Thermal impedance. You can decide between Cower or Foster network for the junction to case thermal interface. You will need to specify the number of thermal resistors and capacitors representing the number of layers. Custom tables and variables. You can create any new variables and even tables in order to use them later in formulas and get a more realistic losses behavior. The values of the custom variables are defined by the user in the device properties. Conduction loss. You'll need to fill in the data necessary for calculating conduction losses. You can decide between lookup table, formulas, and even both. You can add manually each data's temperature, number of points, the datas of the lookup tables, or import them from a .csv file. The graph will be created and modified accordingly. Turn on and turn off loss. You'll need to fill in the data necessary for calculating turn on and off losses. You can decide between lookup table, formulas, and even both. You can add manually each data's voltage and temperature, number of points, the datas of the lookup tables, or import them from a CSV file. The graph will be created and modified accordingly. Once a thermal data description has been created, it can be assigned to a power semiconductor switch, IGBT, MOSFET, or diode, from schematic. Thirdly, let's go back to the overall circuit. As you can see, when selecting thermal datas for both IGBT and diode in the Properties window, an additional pin is added. Conduction and switching losses of a power semiconductor have to be collected and connected to a thermal circuit to determine the junction temperature of the power semiconductor. So the goal of this extra pin allows to connect the semiconductors to thermal circuit and provide the junction temperature as well. Then an orange thermal circuit is designed allowing the user to implement thermal impedance and heatsink network until ambient temperature. Of course, some RC circuits are used for this purpose and measurements such as heat flow and temperature could be checked. Finally, let's click on IGBT component Select all the scopes and run the circuit with original solver settings. We can, for example, display the average total losses and the junction temperature. We can conclude that temperatures of IGBT increases a lot during the simulation and average total losses are quite stable during steady state. All those results are computed because of thermal data entered by the user. Moreover, Delaunay's triangulation and a barocentric interpolation are used to calculate the losses from those provided data. More information about thermal losses calculation could be found on Simba website by going on the documentation section and then click on thermal analysis. This concludes this tutorial video about thermal modeling of power switches feature of Simba.